Hello everyone. The title of our work is Bridging Missing Gaps in Evaluating DDoS Research. I am Lumin. My co-authors are Sam, Devkishen, and Jin. We are from the University of Oregon. Without further ado, let's take a quick look at the DDoS attacks today. Most reported attacks today are easy to detect and mitigate due to their common patterns. However, attacks have started to employ advanced techniques. For example, we see many reports on the posing-based attacks and carpet bombing attacks. We'll present a brief introduction to these newer attacks in the following slides. A posing-based attack aims to flood network links with short and periodic traffic bursts. Here we show a possible link utilization graph during a posing-based attack. The attack traffic bursts are indicated by the red bars in the figure, and we can see the bursts come and go at certain frequency. The detection of such an attack requires fine-grained time series network information. The main consequence of this attack is to reduce the quality of real-time applications, such as online gaming. The attack could also reduce the network throughput of congestion-responsive flows, as implied by the figure. A carpet bombing attack addresses multiple networks of a network. The detection difficulty varies based on the traffic payload and the detection point of view. For example, if the attacker employs the scheme from the crossfire attack, the detection difficulty is way higher than a TCP SYN flood. The consequences are twofold. First, edge networks such as A, B, and C will experience low network throughputs, albeit their inbound links are not congested. Second, since ASX is also a victim of the attack, it may perform DDoS mitigation to protect its inbound link. However, X does not always have the filtering requirements from A, B, and C. As a consequence, X may filter critical traffic towards its downstream networks. Now we list notable DDoS evaluation missing gaps based on our survey. First, while not too surprising, we think DDoS attacks are only going to be more advanced, and we need to be aware of this trend. Unfortunately, we know very little of these advanced attacks in action. Most researchers hardly have access to production traffic and manipulate the traffic. Therefore, to many of us, we need to study these advanced attacks in emulations. Due to the design of the advanced attacks, to evaluate them, many require realistic background traffic or layer 5 application traffic. The second missing gap is to better detection evaluations. As a DDoS detection system is to serve better attack mitigation, we should not evaluate a detection system only using passive network trace. Instead, to claim the soundness of a detection's evaluation, the evaluation needs to be able to answer questions such as how the system handles significant network changes caused by mitigation effort. Such an evaluation requires both realistic background traffic and mitigation system in the loop. Last but not least, we should understand the collateral damage caused by DDoS mitigation. During a mitigation, the victim often knowingly or unknowingly disconnects benign traffic using solutions such as RTBH. In many cases, using RTBH is helping the attacker to finish the attack. While more networks start to adapt fine-grained mitigation solutions such as FlowSpec, routers have limited filtering capacity. It ranges anywhere from hundreds to thousands of filters. Therefore, we often see a victim uses broad traffic matching conditions in mitigation at the cost of disconnecting benign hosts. That is assuming The bot IPs are already validated by the victim. To study the collateral damage, we also need to have realistic IP assignment in experiments. With the motivation concluded, we now introduce our SandBox project. At a high level, the SandBox system leverages the container technology. The design choice comes with many benefits, including but not limited to low deployment friction and elastic system fidelity. Fundamentally, since the container uses Linux namespaces, the overhead to build such a emulation network is generally lower than a virtual machine-based platform. We pack different node images into the system, and once instantiated, we have containers which represent nodes in an experiment. In this system, it is also easy to manage both physical and virtual network interfaces. The SandBox usage model is rather simple. If a user wants a functional network, or defined as a mini internet in our paper, the system only requires a traffic trace or stream. The topology generator will gather required public datasets to build a functional network. Then, the traffic mimicker generates background traffic by reading the traffic trace or stream, and recreates network flows using system sockets. We also include reference node images to represent routers and hosts. In fact, the traffic mimicker is type of end host in the SandBox. Finally, the SandBox driver implements the blueprint that is generated by the main SandBox components above. Here's an example workflow of our system. We first feed the required inputs to the SandBox for generating a blueprint. Then the SandBox driver outputs an emulation network based on the blueprint. The output is what we called the mini internet. In the SandBox, users have the freedom to choose arbitrary node implementations. For example, one can choose Quagga or FR routing for router nodes. The system provides realistic IP address assignments at AS level, and it provides congestion-aware background traffic with the help of traffic mimickers. We evaluated our PLC system from two aspects: the correctness of the topology generation and the scalability of network instantiation time. Machine specifications and software environments are listed in this slide. In the correctness test, we run a trace route from an educational network to a major cloud provider. Note that all router interface IPs are populated by the SandBox automatically, as indicated in the screenshot. Since we didn't apply any traffic control policies on the network interfaces, there is little delay from hop to hop. If we transfer the router level paths to S level paths, the S level paths can be found on websites such as BGPView, while our trace route result does not reflect the real-world paths. It adds more realism to the experiment and helps users to run better collateral damage evaluations in DDoS mitigation. We then run a scalability test to understand the limit of evaluation machines. In this figure, we show the relationship of system instantiation time and the number of launched routers in a single host setting. We find the 3-core machine with 24 GB of memory can support around 100 routers before running into memory swapping issues. Meanwhile, the AWS machine with higher memory space continues to follow its linear trend. The SandBox project is an ongoing work. We are integrating the traffic mimicker, DDoS attack, and defense projects into the SandBox. In particular, the traffic mimicker implementation is not a trivial component. And we ran into many design challenges that we did not cover in this short paper. To have better system scalability, we plan to distribute container nodes across a cluster of machines in order to support for more end hosts, as well as to better network realism. In this POC, we used ContainerNet as the SandBox driver. We are considering to use other solutions that could have better support and system compatibility. For example, one of our paper reviewers suggested CNI projects, and we find them to be quite promising for managing network interfaces in the SandBox. In conclusion, we presented a list of evaluation missing gaps in DDoS research. We introduced the SandBox project, a container-based emulation system. The final goal of this project is to create an open-sourced repository, well-received attack and defense projects, and evaluate them in more realistic settings. Thank you. We would love to hear your feedback. If you have any question, please feel free to drop us an email.